Good evening. Thank you for that. My name is Will Shackle. I'm the founder of Nuclear for Australia, and this evening we're thrilled to welcome you to our information evening. Particularly, we'd like to acknowledge those in the room, the Mayor and the select councillors who've made the opportunity to visit this evening. For those who aren't aware of Nuclear for Australia, we are a non-partisan nuclear advocacy organisation supported by tens of thousands of Australians across the country, including many in this room. We've decided to hold free events like these across the country so people can learn the facts about nuclear and hear from some of Australia's best experts. Before I hand over to Jonathan, who will be the MC for this evening, I first wanted to go through some basic housekeeping. Firstly, we appreciate that there are many opinions on this topic. As Jonathan will address, in addition to the questions which have already been sent through to our experts, and let me just say, I think there's been over 100 questions sent through this evening, we will also have the opportunity for you to send in questions throughout the evening if, in case our experts have not addressed the concerns or questions that you have. There will also be an opportunity to talk to one of our experts at the conclusion of this evening, and if we are there at that point not able to have addressed your questions, you can also contact Nuclear for Australia using the email on our website at nuclearforaustralia.com, and we'll endeavour to get back to you. Secondly, please note that this event is being recorded and photos will be taken. If you do not want your photo taken, please let whoever's taking photos know, and we'll make sure that you are not in those photos. And finally, in the event of an emergency, please head to the exit at the back of the hall. Our team will also be able to provide assistance if you need it throughout the evening. With all that said, thank you again for joining us. I'm now going to hand over to Jonathan Fisher, the CEO of Coolgin Energy. Thank you.
Thanks, Will. Will's a bit too good at that. He's going to do me out of a job. Look, thank you. Welcome to the Nuclear for Australia information evening here. I'm very pleased to be the MC for tonight. My name's Jono. My mother calls me Jonathan, but my friends call me Jono. And I'm here to introduce these wonderful people. I don't consider myself necessarily an expert on much, but these guys certainly are. And so we're going to spend a bit of time talking about the key issues that many of you have taken the opportunity to send through your questions. Is this not working again? There we go. Okay, so many of you have taken the opportunity to send in a question. If any of you have a question you want to ask, this is a fantastic thing with the interwebs. You can take a photo of that and actually we can try and address it and live upload it to our question list during the night. So I'll leave that up there for 2 seconds. I just want to talk a little bit about myself, my experience in the nuclear industry. I'm here because I think nuclear is the right thing for this country. But I've also got a fairly broad background across the radiation space. So I do run a uranium company. My passion is to overturn uranium bans that are current in WA and up here in Queensland too. I previously also bought and sold nuclear power stations in the nuclear industry in the UK. And then I was the one who actually did the approvals and financing for the radioactive waste repository that Australia now has operational in WA. It's a fantastic facility and it is actually a national treasure and a competitive advantage for Australia, but I won't get into that. But you know, how I ended up on this journey is quite interesting. Growing up in Australia, I knew nothing about nuclear, right? I found myself quite by accident in the nuclear industry in my late 20s. Now, I grew up in Australia, they didn't teach it at school, so I learnt from The Simpsons. Yeah, right. So what we're probably going to find out today is that is not the best place to get your information from nuclear for. But the problem with, and I'm sure a lot of you did the same, come on, you can put up your hands. The problem with getting information from these kind of TV shows and other things is that you're not actively going out there to seek that information. It kind of creeps into you as subconscious bias, right? And that's quite different to you actually coming out and saying, hey, I want to be informed about a topic. And it often can come to the wrong conclusions. I'm going to tell one very self-deprecating story here. I haven't warned the guys about this. So picture me, I'm in my early 30s by this stage in London. I'm in peak condition. That'll become relevant in a second. Tony, I'm going down to Dungeness B, which is a nuclear power station in the UK. This is about the time that my wife and I were trying to get pregnant for our first baby. And my wife comes up and she's stressed. And I'm like, what is it? And she's like, well, are you going to be wearing lead undies? Because you've got to protect your boys, your swimmers, right? And I'm like, what are you talking about? Well, it so happens that there is a particular episode of The Simpsons where nuclear energy was literally blamed for Homer's lack of fertility. And this is what my wife was she's going to kill me for saying this. She's an incredibly smart lady. She has a PhD, yet she was very worried about my boys. So I can safely say, thankfully, I've got 3 kids, no troubles in that department. But perhaps it's a good idea to come and actually seek out information from experts than rely on The Simpsons. So with that, okay, we have 3 experts with us, and the first up is Stephen Wilson. So I will tell one thing about Stephen, if that's all right. Adjunct Professor Stephen. He is what you call an energy economist. So his engineering friends think he's an economist, and his economist friends think he's an engineer. He's got a bit of a crisis of confidence and identity. He doesn't know who he is. But he is the key author of the key report, What Would It Take? What would be required? Which is a report that actually does the work and says, what are the things we need to do to implement a nuclear industry in this country? So with that, I will turn over to Stephen.
Thanks, John. Thanks very much, Jono, for that kind introduction, and thanks to Nuclear for Australia for having us here, for inviting me, and thank you all for coming along. I'm going to go for a bit of a wander. That's me. I'm an adjunct professor these days at the University of Queensland. I was a full-time professor for 3.5 years. I'm now out in the wild at large. And as Jono said, it was several years ago, back in it was just before the pandemic actually, and Barry Murphy came to me and he took me to lunch at the Regatta Hotel and sat me down and said, he told me his student drinking stories, and then he suddenly went serious and said, Stephen, what would be required for nuclear energy plants to be operating in Australia from the 2030s? And I took a deep breath and I said, Barry, that's a huge question. He said, I know. I said, as a matter of fact, it's 7 questions. And he said, do the study. I've already spoken to the Dean and the resources are there to do the study. So we got to work. Turned out there are 8 questions. The answers to those 8 questions are 8 chapters. You can find this report on the university website and download it. Just Google what would be required, nuclear UQ, and you'll find the report. Big conclusion, which was a learning for me, is can we do this in Australia? Yes. If we put our minds to it, we are quite capable of doing this. I'm slightly embarrassed to admit I thought it was all too hard and complicated for us. That is not true. The big recommendation of this report is, regardless of what anyone thinks about this question, we need to create the real options. We need to do the preparation work to be ready, to be in a position to start building nuclear power plants if we decide we need them. And that's really what this report is all about. I'm just going to show you a couple of charts here. For many people, not necessarily everyone, certainly not everyone, and not necessarily me, but for many people there's a concern here about climate and emissions. And I just want to show you at the top is basically saying that's the theory that sits behind the idea we must reduce emissions and nuclear is a way to do that. The chart on the left is, I think everybody agrees on that. I've never heard anyone question the measurement of CO2 in the atmosphere on the top of the mountain in Hawaii. That's the actual data up to the latest available data of the concentration of CO2 in the atmosphere. It's just continuing to go up. That's just the reality. And the chart on the right is the chart of temperature. Again, I don't think anyone questions the measurement of the temperature data from the satellite. So we could talk about that all night. We're not here to talk about that. I just want to put that there for context. This is a chart of Australia's CO2 emissions starting from 1990 up to a recent year. Most of it, but not all of it, is energy. And that's, I've highlighted the last year there in red. That's the energy piece. Some, but not all of that, is electricity, 165 to 420 tonnes. The chart is indicating what our government has promised we will do in the international arena. You can see that that is a very, very dramatic and challenging set of targets that have been agreed, that have been promised. Who's got solar panels on their roof? Cool. I didn't put my hand up because we don't. I'm in Brisbane, but Mum and Dad do, so that's Mum and Dad, and that's the house I grew up in down on the Bellarine Peninsula. So I don't want anyone to think I'm sort of bashing solar energy or solar panels throughout this talk. Some of my best friends have solar, and my family. We hear these words very often, we need. Every time, and if you want to hear a little bit longer talk on this, look up the talk I gave at James Cook University in Cairns earlier this year. Whenever you hear the words we need, I want you to ask who is we and what is behind this word need, because I think a lot of the time it's you must is the subtext. So I think we need to question this assertion that's made over and over. What we're being told we need to do is cover vast areas of Australia, rural areas, natural environments with this technology, wind turbines and solar panels. This is a quote from the former Chief Scientist, Dr. Finkel. When you do the numbers, which people have started to do, the Net Zero Australia report is an example, what you find is that if you're going to try and achieve that carbon reduction goal just with this technology, the land impacts are just absolutely enormous. This diagram is showing the capacity stack of existing power generation on the Eastern Australian system, Queensland, New South Wales, Victoria, South Australia. We're stacking up from the brown coal in Victoria, the black coal in New South Wales and Queensland, and then we've got various types of gas generation, hydro through the middle there, gas turbines, and then the wind and solar farms. The red line is kind of roughly where we are now, and that decline in the coal fleet is what we're being told is the retirement schedule of this fleet. The reason I've not allowed those upper parts to come down and fill the gap is because I don't believe that any of that technology is capable of filling that gap. Even the hydro can only run a fraction of the time. There's just not enough water in the Snowy system to cover that. So that gap is absolutely enormous. I don't think those plants will end up being retired on the schedule that is being told, and we've seen the first example of that in New South Wales when the state premier, the new Labor state premier, Mr Minns, basically told Orano, you can't close when you announced, you have to stay open for at least another 2 years and possibly another 2 after that. I think that's the first example of this phenomenon. This is just showing you the various coal units that we have in Queensland, New South Wales and Victoria. We have some small ones down in 280 size range, and then all the way up to the largest unit in Australia is Kogan Creek in Queensland, 750 megawatts. I've highlighted here for you the Tarong Power Station and Tarong North Power Station just down the road. 4x350 for 1400 megawatts on the 443 at Tarong North. I've just mentioned Eraring in New South Wales has been told it needs to remain online for a bit longer. Liddell, of course, was closed in recent times. That's what we need to replace. AEMO is publishing these retirements, and they're just pushing this curve further and further to the left. I think it's completely unrealistic. What they're proposing to build in its place is a vast system of overbuilt wind and solar capacity The hydrogen superpower, I think, is complete fantasy for other reasons. So let's focus in on the lower part on the left. I've enlarged that on the right. What you'll notice here is, this is from the 2022 Integrated System Plan, is that there's very little dispatchable, what they call dispatchable capacity is not like the system that we have today. It's made, you can see what it's made up of in the magnification there. Peaking gas and liquids plus hydro, and then storage, and storage, which is assumed that you and I and everyone else will pay for, and they won't count the costs in the analysis. This is comparing on the left the 2024 latest version with the 2 years ago version. There's a lot of changes happening. They're admitting that we need a lot more gas, a lot more peaking gas. Data Western's on record now saying that, than what was being stated just a couple of years ago. In terms of cost, we are being pushed to a more and more expensive system. We grew up with a system I'm describing, a coal-based system that is on the order of about $50 a megawatt hour, 5 cents a kilowatt hour, wholesale on the bus bar. Moving to a system where gas is setting the price much of the time. If gas is priced around $10 a gigajoule, you'll have a system wholesale around $100 a megawatt hour, 10 cents a kilowatt hour. If you try and do everything with wind and solar, you're up in the region of double again. So we've sort of doubled the cost, and we're doubling again. And then just remember that that's only a fraction of the cost. So the piece on the left there, wholesale costs, that's what we were just talking about. Then you've got all the network costs, the transmission and the local distribution. So we're talking about sort of doubling and doubling again the costs of delivered power to customers, to households, and also to businesses. I just want to say at this stage, I used to be anti-nuclear. I grew up during the Cold War. I was conditioned, like Jono was describing, with a lot of these ideas. It took me 35 years for my mind to change on these things. I've seen other people change their minds very quickly. Steve Nowakowski, he said it took him 2 months. He just did his own reading and he changed his mind in 2 months. He's clearly much smarter than me. But I would never be sort of rude to anyone who's struggling with these issues, and I think we all need to talk about these things with each other. The Brisbane Dialogue event in August last year, that's available on YouTube. You can see that conversation. There's a more recent one that I participated in down in Melbourne. The issue of cost will come up, and I use this provocative framing here. It is very important that if we go to nuclear, that we don't mess it up, and that we work out how to build these plants as efficiently and cost effectively as possible. It is possible to mess that up, but in Australia we have actually got a record of building a complex nuclear reactor on time and on budget, and the man who commissioned that plant is here with us this evening. So we need to look at the lessons from around the world, work out what we need to do in Australia and how we need to do it, and have some confidence in ourselves. Jobs is a concern for people. In the UQ report on page 18, you'll find a reference to some work that shows that jobs in coal-fired power plants translate across very well into nuclear power plants. It's not that everyone in a nuclear power plant is a PhD nuclear engineer. There's a lot of common jobs. This chart, which we borrowed from Jasmine, she sourced that from the US DOE. This shows the different types of jobs in coal plants and in nuclear plants with different levels of skills and education. So you can see that only a few have PhDs, some have master's degrees. You need some more of those in nuclear than you do in coal, but the bulk of the roles in the power plant, from associate degrees, some college education, high school level education, is very similar from a coal plant to a nuclear plant. And I'll just close with this before I hand back to Jono and over to Tony, which is the idea of a nuclear mindset and the concept of responsibility in this safety critical industry is very important. And this is a quote from Admiral Rickover, who conceived of and invented and developed the first nuclear reactor, practical nuclear reactor, and squeezed it into a submarine and put to sea. And he went from the question of, is this even possible, to launching that submarine with the reactor on the sea trial. All of that work was done in less than 10 years. So if people tell you that it takes us more than 10 years just to set up our regulator, for example, you've got to examine that. You know, that's just a crazy assertion. These things can be done in a timely and efficient way with the right people and the right attitude. And if we're going to do that as a country, it will lift the whole capability of the country. And so I think the concept of responsibility is something for all of us, for each of us to play a role and take part in this conversation. Thank you very much.
Okay. Well, good. Where's the clicker? There it is. Clicker. Fantastic. Okay, so next we have Tony Irwin up here. Now, Tony has a distinguished career. Tony and I both actually used to work on the reactors in the UK. You can probably tell that Tony did a little bit before I did. But Tony has experience in 8 reactor commissioning and operations, and they're big ones, as well as commissioning Australia's only operational reactor, being the Opal reactor in Sydney. Tony's also the chair of the nuclear engineering panel for the Engineers of Australia. So you have here Australia's foremost mind and most experienced person in commissioning reactors, so he can tell you how it can be done safely.
Thank you, John. So, I'm an engineer. I spent more than 30 years in the UK commissioning and operating big nuclear power plants. And then I was fortunate enough to meet in Australia in the UK. So in 1999 we came to Australia. I joined ANSTO, and I was reactor manager for the Opal reactor during all the commissioning and early operations. Pressurised water reactor. This is a pressurised water reactor. So this is the most common reactor worldwide. 70% of reactors currently operating, 90% of the new ones being built. It's the same reactor in a mini version that's in the nuclear power submarines. Who works at Toronto Power Station? If you work there, you will recognise all this turbine, condenser, feed pumps, etc. So this is all a nuclear power plant is exactly the same as a coal-fired power plant. This is why, if you're a turbine operator at Toronto, you could be a turbine operator at a nuclear power plant. It's basically all that is the same sort of equipment. So all it does is generate steam. The way that it does it is through the nuclear reactor rather than burning coal. And it all starts with this. This is a nuclear fuel pellet. It's about the size of your little fingernail. And this is entombed in the reactor, and this is producing all the heat. And this is equivalent to a ton of coal. So this is a really high density, very efficient sort of circuit. So a pressurised water reactor has got 2 circuits. It's got a first circuit that takes the heat from the reactor, and then it transfers it to a steam generator. So the reactor circuit is separate from the rest of the plant. So all of this part isn't radioactive. It's only in that self-contained circuit. And then when we look at we'll worry about water use. This is a closed circuit. Small amount to top up. This is a closed circuit again, just the same as a coal-fired power station. So this is the water usage. So it's exactly the same as you've got at the moment. The main water usage is condenser cooling. So at Toronto at the moment, we've got cooling water there, so we can look at a bit more detail later about cooling water. For those that work at the power station, if you look at the steam conditions here, 7 MPa, 275, you'd say they're awful steam conditions. It's a much, much lower temperature. The coal-fired power station is far better steam conditions. And then of course it goes out on the grid, and terrain has increased in size a bit, you can see that. There's concerns about, well, house values go down. No, they don't. They go up around nuclear power plants. With sewer plants in the UK, and you can see it everywhere because it attracts industries and it attracts well-paid jobs, etc. So is this radioactive waste, this green goo? Well, fortunately, it isn't. So radioactive waste that we transport and move around is always solid. Day-to-day operations just produces this low-level waste. So it's this sort of materials, this cleaning materials, clothing, resin, filters, etc. It goes into drums, goes to a drum store. You can stand beside these. This is the Ansco drum store. It's very low level. So a big reactor, that's a 1,000 megawatts, 2 shipping containers a year of this low level waste. And then it goes into a repository. So we've got a low level waste repository in Australia. This is the Talis Sandy Ridge facility in Western Australia. And it's licensed to accept low level waste from anywhere in Australia. So we've got a proper low level waste to international standards. So the main concern with waste is the used fuel. So when the fuel is out of the reactor, it's very hot and it's very radioactive. So everybody immediately puts it into a pool of water for 1 to 8 years. So the water provides shielding and it provides cooling. So you can actually stand beside a cooling pond, look down in the fuel, and you're quite safe because you're shielded with the water. And then we've got 4 options: dry casks, reprocess, disposal, or used in an advanced reactor. So this is dry casks. So a lot of power stations take it out of their cooling pond and put it in a dry cask. So here's the fuel assembly. It goes into a big steel cask, which is got on the outside of it, concrete cask. And it could stay there for 100 years. About 1 year's fuel in each cask. So you can have that on site, and certainly in the US, and a lot of Europe, and all of Canada, they just store it on site for the life of the reactor. Or you can reprocess it. So 96% of fuel assembly can be recycled. So you can remove the uranium and plutonium, and this is what they do, particularly in France. They recycle the fuel and they use the plutonium for what they call mixed oxide fuel. It goes back into the reactor. And they save quite a lot of uranium by doing that. But it also reduces the volume, reduces the time to decay. You can vitrify the waste. So it's quite a good long-term solution. So all the fuel from Ansco's reactors goes to France. It's reprocessed, and we get the waste back just as intermediate level waste, not as the high level waste. If you've got high level waste and we want to dispose of the whole fuel assembly, then international best practice is this deep geological facility. So this is the one in Finland, and it's in the final stages of commissioning. They're actually doing trial runs, so it's all completed construction. So it takes the fuel, and puts the fuel into a copper canister, and then the copper canister is buried underground, surrounded by bentonite clay, which stabilises it and stops moisture coming out of it. So this is about to go into operation. A similar one is this, let's say, in Sweden and France are quite well established as well. So that's a brief introduction to nuclear power and waste.
Okay, next up we have, we've got our clicker, Rob Barr. So Rob is an engineer and is an absolute expert in electricity systems, to the point that he's received a Member of the Order of Australia for his services to the electricity industry. So you can absolutely believe what he says. Over to you.
Thanks, Jonathan. Well, it's a pleasure to be here tonight, a pleasure to come up to Queensland. By background, I'm a consulting engineer. I've spent all my career basically providing low-cost, reliable electricity to customers throughout New South Wales and Australia. And how do you think I feel at the moment with the situation of the power industry? It's just a complete, it's really gone off the rails in the last 10 or 15 years, and I'm just so disappointed with the situation that we're in at the moment. By way of background, my clients are electricity distribution companies. I do work for Ergon, which you would all know, and Energex here in Queensland, many other distributors across Australia. And most importantly, I also do a lot of work for high voltage electricity customers, the big customers that make gluten, starch, ethanol, oil, even cement and the like. So I get to see the whole electricity system in its entirety. So we're up here. I'm going to give you a little bit of a background of how I think things are progressing, and things are not progressing as well as they should. But you've got a very valuable resource here in Queensland, the Tarong Power Station, the 400 megawatts plus the 443 megawatts for the second unit, is a very valuable resource that's going to be very important to the future of Queensland, and not just Queensland, to the whole nation, to me down in New South Wales and the rest of the national electricity market. So, I'll just get this right. So why is it important? It sits up here with there's Tarong up there, and the power stations down in this area. It sits close to Brisbane, and it's got a very strong transmission link. And this is a strategically important asset that's going to make Tarong important, not just today, not just for the next decade, but for the next many decades. So why is it a good site for a nuclear power station? It's the strong link to Brisbane and to the rest of the national electricity market that's going to make it very, very important. So, there we go. But what's going to happen to the existing coal plant? It's going to come to an end of life, like many of the others. Wallerawang, this is a site of what happened to Wallerawang with the destruction of the towers. Wallerawang is no more. There's Mount Piper in just west of the Blue Mountains in New South Wales, where it's still in operation. But these power stations are going to come to end of life, and we need to make sure that there's replacement. And the obvious replacement for the Tarong power station is a nuclear power station. So, now, where are we with the NEM at the moment? This is work I've been doing with modelling, and if you look at this is a load profile of the national electricity market. This is megawatts on that axis and time across there each day. So what we find is that in the middle of the night, 2, 3 a.m. in the morning, the load is down, it comes back up in the morning, goes back down. We go through this cycle. Many of you would be familiar with this cycle. But what's happened in the old days with our brown coal down here in Victoria, our black coal, we've now introduced so much solar into the system that it's pushing down into the black coal area. So the black coal stations like Tarong and Mount Piper and the brown coal stations also in Victoria, they're unable to generate in the middle of the day because they're being pushed out by solar. This is a very important aspect of what's occurring. And what it's doing, it's destroying the business model of the coal-fired power stations in Australia. And that's why these plants are closing down. So what we have is what I call the net zero renewable stream. This is what we're aiming for. But unfortunately, it's unravelling. Who heard the promise of a $275 reduction in electricity bills? Now, when the now government, then in opposition, put that forward, they were very confident they could achieve that because they had a Reputex report that forecast that with the way things were being planned, that electricity costs would fall. And that hasn't come to pass because I believe that report was flawed. The main flaw in it is the integrated system plan that the government are relying on. The integrated system plan, to me, just does not stack up. It technically doesn't work, it commercially doesn't work, and one of the main reasons it doesn't work is it doesn't include all the costs. It doesn't include the cost of rooftop solar PV, behind-the-meter batteries. It doesn't include the costs of the distribution augmentation that's required. And when you add up all those costs in their plan, it's more than half the costs. So when they've analysed the costing of their renewable plan, they have excluded some of the most important costs. And it's no wonder that things have gone off the rails since. And my prediction is that the costs, if we keep going in the same direction, the costs will just keep climbing. So there's urgent need to change direction to prevent total industrialisation. I've seen the effect this is having on my big industrial customers, and they're just overwhelmed with electricity costs. And the medium-term reaction is to give it away, and if you've got alternatives to produce output in other countries like the US or Europe, they will take that. And that's why we're going through this process of deindustrialisation, and I believe it needs to stop. So, that's it. Now let's have a little look at what the problem with the renewables is. I call it this summer abundance. Same curve as before. This is the load curve. But this is what a 100% renewable system would look like in 2050. What happens is that the load curve is there like it was before, up a little bit higher, and then we've got this brown colour here is what I call spillage. Spillage is electricity that can't be used because there's no customers there that need the power at that particular time. Then we progress through day by day. This yellow area here is electricity going into storage, and then that storage is then used later on in this particular area here, but we've got more spillage. So what we end up with a renewable system like this in summer with solar PV, we just end up with an overabundance of electricity, a lot of which we can't use. And then when we get to winter is where the things get really tricky because the days are shorter, the solar generation drops off, and then all it takes is a coincident wind drought, and we end up with a situation here. This is a situation where there's just, this system's on the verge of failing. We've got pump storage working here, we've got batteries coming in, and we're just able to scrape through these particular days to supply the customer needs. So, but this is a very, very unstable situation and very expensive because we've got to provide all the resources to provide this extra supply in the middle of the day that customers can't use. Now, I will go forward to what effect does this have on transmission? Because the generation costs, it's not just generation as such, it's also transmission and distribution. And I put this slide together. This is a New South Wales slide. If we consider the Sydney situation here, where most of the big loads in New South Wales are in Sydney, and if we build a renewable energy zone up here, what I what I'm talking about here is the existing system. We've got Sydney Load, we've got the Hunter Valley Power Stations with strong connections. We've got Dullo out here, which is a regional area like we're here at the moment. And we've got Mount Piper, we've got Canberra, and we've got Snowy Hydro. Fast forward to 2050, the Hunter Valley Power Stations are closed, so these lines can't be utilised. We then have to have a renewable energy zone at Dubbo, but you'll note from our previous slides that we produce a lot of excess power in the middle of the day, which has to go into storage. But the storage is not at Dubbo. The storage is down here at Snowy Hydro, Snowy 2.0. So we have to build transmission lines down. And then what we have to do then is have another transmission capacity to bring them back to Canberra and to Sydney when the sun goes down. So what we've done through this sort of process is massively expanded the transmission network. And this is one of the reasons the costs are going so high. And it's similar things are happening with the distribution network as well. So what's the alternative? If we go nuclear, this is a site that I visited in Darlington in Ontario, Canada. And they're in the process of building a nuclear power plant on this site here. And this will be a small modular reactor, and I'm hoping that it will become the model for what we can produce here in Australia. So what would a nuclear system look like? If we look at nuclear base load, what we have is our load profile like we had before, and in its ultimate form, your base load will push right up here to the bottom of these troughs. And then what we can do, we can still utilise the renewable solar because it comes in the middle of the day and works and fits in quite nicely with the peaks in the load, and we can produce a very successful system. So the point I make is that the solar and wind resources that we have at the moment can be married quite well in with nuclear. But the thing is to not overdo the solar and the wind, and that's the problem that's occurring at the moment. If we were to stop doing it now, or take away the subsidies so that only commercially viable wind and solar plants would proceed, we're going to end up with a system that can work quite well. And this is a system that would look something like this. So, in summary. As we move toward net zero, as net zero is the plan for many for governments, we need to recalibrate public expectation. We need to make it very clear that the $275 a year reductions are not achievable in the short term. Achieving net zero is very difficult, very expensive, and can't be achieved in the short term. It requires new thinking. Delivering reasonable price electricity with net zero, I don't think can be done without nuclear power. And this is where the Toronto Power Station is going to will have a role in the future. I just conclude by saying nuclear's got a very key role to play, and Toronto's got a key role to play. You're in a strategic location here on the national electricity grid, and I think it's the transition to nuclear here will open up new job opportunities for existing workers that are working at the Toronto station, and it's going to operate, it's going to provide new opportunities for other skilled people in the future. And with all that information, I just hope that the people in this room will consider the benefits of nuclear for Australia and for this area, for this part of Queensland as well. Thank you.
So, we had a lot of questions, and we have had someone actually listen to me and lodge some questions during the speeches, so that's fantastic. So, what we're going to do now is going to be like a TV dating show. I'm going to ask a question and try and match it up with an expert. We have tried to answer everyone's questions. Some were duplicated, so you might notice that the question up there is sort of similar to yours, but not the exact wording you used, so please bear that in mind. Secondly, if we don't get to your question and you feel your questions weren't adequately covered in the presentations or during these questions, please do email us afterwards and we can get back to you. Okay, so do we have Jess in the room at all? Jess? Oh, there you go. Okay, well, Jess, I hope you asked if it was you. How much water does operating a nuclear power plant require, including that held in reserve for emergency use, and where will the water come from? Do we need another dam? Experts?
So as I showed with the PWR drawing, the main source and need for water is the turbine condenser. So it's exactly the same as a coal-fired power station. So does a nuclear plant need more? As I showed you, it's slightly less efficient than a coal-fired power station. So for any given sort of output, it'll need slightly more than a coal-fired power station. But if, for instance, you looked at Tarong, now you've got a 30 gigalitres a year water allocation for your 1,800 megawatts. So you could put, say, 1,100 megawatt nuclear power station on the same site, and it would use less than that water allocation. So that there's no huge difference with a nuclear power plant. As far as the water required for the safety of the reactor itself, so that primary circuit, the first circuit, you see that all sits in a very big containment. So within that containment, it's got its own water tanks. And modern reactors now have what they call passive safety systems. So in the event of a problem where you can't get rid of the heat to the secondary circuit, then you've got the water tanks in the big containment. You don't need outside electrical supplies, you don't need outside water supplies. So this sort of reactor now survives even the Fukushima type of incident. You don't need any attention to it, it'll keep itself cool with that system. So cooling water is not a major problem for transferring from a coal-fired power station to a nuclear power station.
Thank you, Tony. Okay, Anne, do we have an Anne? Maybe we've got more than one Anne. Anyone? Okay, well, Anne did ask, where and how will the nuclear waste be stored? And Tony, you did mention that in your speech. I also want to give another shout out to the Tellus Sandy Ridge facility in WA, which I'm very passionate about. Cracking facility. But Tony, the rest of the nuclear waste, the higher level waste, I'll just make a couple of comments before I turn to you. We are progressing AUKUS in this country. We are going to have a fleet of nuclear submarines as part of the AUKUS agreement. The federal government is obligated to site a higher level waste repository. So that will happen regardless of civilian. Now, okay, having built a radioactive repository, that's me. Once you've built one, you want to put as many tonnes in there as possible because then it reduces the average tonne, the cost of the average tonne going in there. And so it makes a lot of sense to have your civilian waste co-located with your AUKUS wastes. They may be physically separated because the Defence Department likes to have it on what's called the Defence Estate. But so they may be slightly separated, but most likely the same facility. Tony, anything to add?
Yeah, so we've been safely managing radioactive waste for more than 70 years. And as we've seen, we've got 4 options for managing it, and different countries choose different options. So places like France decide to reprocess it, recycle the fuel, reuse it. Other countries like Canada and USA decide at the moment, although they are reconsidering at the moment, but they haven't been reprocessing. So they're looking for some long-term facility. So at the moment they're using the dry cask facilities. But I think everybody's very interested in what's happening in Finland, because that's the first deep geological facility in the world that's going to go into operation, and this is really going to be the proof that that's international best practice for the long-term management of high-level waste. Few interesting concepts as well. Borehole technology, we're now very good at drilling down deep and turning the drill and going horizontally. So there's a company in the US called Deep Isolation that's done a lot of testing on this. And it's quite possible that for countries with smaller amounts of used fuel, like Australia would be, and like with the AUKUS programme, that borehole technology could be the answer for this, because you can put it down sort of 1 kilometre deep and really well isolated for a long time.
Stephen?
Yeah, just to add very briefly to that, Jono, I just want to say that, and this is the saying of Xeon Lights, who gave me this T-shirt, it's only waste if we waste it. So the point that Tony made in his presentation about reprocessing, it's future fuel for our children and grandchildren. So the bit that's the nasty stuff is very small, and we can lock that away, but the used fuel can be reprocessed and used again in future generations. Very valuable.
Yeah, and I think it's a good time to note that nuclear waste is obviously a question that we get a lot, and so Nuclear for Australia has done a fact sheet specifically on nuclear waste. So if you go onto the website, you can download that, and there is a lot of information on that specific topic. Okay, Janet and Warren. The exclusion zone. Okay, how far is the exclusion zone from a nuclear power station?
I might address this briefly, and then Tony can add some expertise. In the UQ study, this is one of the things we talk about. So in the United States, for big nuclear power plants, they have very large exclusion zones. The new technologies that are coming, the SMR technologies, for example, the NuScale 1 is licensed so that the exclusion zone is at the fence of the power plant, which is a very, very small area, about the size of the Circle of Parliament House or about the size of the University of Queensland campus.
So when you're planning a nuclear plant, what you have to do is a safety assessment. So you produce what's called a safety analysis report, and this looks at all the things that can go wrong, internal events, external events, and how your power station will cope with those events. We're now getting to the stage where we've got reactors that have got this passive safety. They don't need backup diesels, they don't need external water supplies. The safety is all self-contained within the reactor. And a lot of these are smaller size ones as well. So obviously if you've got a smaller size reactor, there's less radioactive material there, so that makes it easy as well. So if you've got a smaller size of reactor and a passive safety system, then you can get down to the stage where the exclusion zone is literally the site boundary. So the NRC, the Nuclear Regulatory Commission in the USA, have looked at the NuScale plant design and said for this design there doesn't need to be an exterior exclusion zone, because the safety of that plant is so high that you don't need to go beyond the site boundary.
Thank you. Did I skip on there? Okay, from Gregory. Greg, anyone? Okay, well, Greg said, are we aware that the Tarong Power Station is built on a fault line? Obviously, earthquake question, without saying earthquake to it.
Again, one of the first things we do when we look at siting is the geotechnical survey of the site. So there's the international standards that everybody in the world works to. So you look at the fault situation in the area and then design the reactor to live within that fault situation. As an example, Fukushima plants in Japan, that's in a very high seismic activity area. So that plant was designed to withstand an earthquake. What it actually got was a 9.0 earthquake, which was the world's 4th largest earthquake. But that didn't damage the plant. So the plant successfully shut down and did all the initial cooling and was quite okay until the tsunami hit it later. So even in that extreme situation, the plant is not damaged by an earthquake. The Richter scale is a log scale, so the typical ones that we're hearing about in, say, the Hunter Valley are scale 4. Scale 9, you know, that's 100,000 times as bad an earthquake. You look at Australia generally, and you know, it's not a problem at all to design a nuclear power plant to deal with the sort of seismic conditions we've got in Australia. But it's something that you do in detail to international standards when you go through the whole of the siting process. We did this with Opal. So Opal had to have a seismic assessment. Opal's got seismic trips. So there's detection systems in the basement of the reactor. If it did detect an earthquake, it automatically trips the reactor and makes it safe. So we do that on every reactor anyway.
Rightio. And I take it we're not going to get a tsunami here. Kingroy. Right, from Linda, if Linda is around, how safe is nuclear? I live about 5 k's from the Tarong station.
Yeah, so there's 2 things we have to do to make a reactor safe. So the first thing is you want to stop the fission reaction, the chain reaction that's keeping it going. And that's the easy bit. You put in the control rods, they mop up the neutrons, the chain reaction stops. That's the easy bit. What you then have to do is remove the heat that's still being produced. This is what they call the decay heat from the system. This is what killed Fukushima, because they couldn't remove the heat afterwards. So this is why it's so important with all the modern power stations that they have safety systems that guarantee you remove the heat. There hasn't been a reactor built in the last 30 years that's had any incident that's not been able to remove the heat, because all the modern ones are built on these sort of systems that guarantee the heat removal, and then the reactor is kept safe.
And just for everyone, when was Fukushima built?
So that was 60s design, built in the 70s.
Right, so a bit different to a 2020s design. I think this is one for Steve and Rob. What other technologies are best to work with nuclear to reach net zero?
Well, the first thing to remember is that nuclear is dispatchable and provides a base load capability. So when we look at alternatives, we're trying to do exactly the same thing. And can we do that with the alternatives? And let's just quickly go through them. Wind and solar, of course, they're intermittent, and to produce that base load capability, they require an awful lot of storage. Is it technically feasible to do it? I say it's theoretically possible to do it, but economically probably not viable. And that's the situation that we're heading for at the moment. Other alternatives in this space, we've got geothermal. So you need to have a very special set of geological conditions to do that, and they've done that successfully in New Zealand. We've tried it, I think, in South Australia, and that hasn't worked out so well. So for us in the eastern part of Australia, I don't think that's going to work for us. There's wave power. Wave power hasn't been that successful. It's intermittent and very difficult to scale. There was a wave power machine prototype built at Port Kembla down near where I live in New South Wales, and it lasted about 6 months until a big storm came through, and we all have our little engineering disasters. I've had my fair share. So there are issues with trying to harness power from waves, and particularly being able to deal with those worst case events. And the other one that comes to mind is tidal power. There's some parts of Australia where there are very large tides, particularly up in the northwest and maybe top of Queensland as well. but you need very special conditions to be able to do that. And again, it won't produce power at the times that you necessarily want it. Sometimes it will, sometimes it won't. The good thing about tidal power is it's predictable. So are there alternatives? Yes, but I don't know that they're anywhere near as viable as nuclear.
I'll just add a comment there. So there's one of the things that I'm hearing very often is that nuclear energy cannot work together with renewable energy.
And doesn't load follow, yeah.
And because the idea is that it can only run in a constant output mode. I used to think that was the case. It turns out that's not true. Reactors these days are designed, they can modulate their output to a very significant degree. I then thought that it was not economic to do so, but when we did the research, when we modelled the national electricity market, we found a result that surprised me was that you can modulate nuclear to a very large degree together with a certain amount of wind and solar in a balanced mix, and that will give you the lowest cost outcome.
Paulette asked, how will a nuclear station affect our home prices? Aussies love our homes and real estate investment. Will it go down?
I don't think it will make prices go down. Tony's mentioned this in his talk. I think if you look at the land and the house prices around the Opal Research Reactor in Sydney, you'll see that they're very, very strong house prices, and that the people who live close to that reactor are very happy living close to it. And we see similar things in other parts of the world. Basically, a nuclear power plant's a very good neighbour.
Well, and I think driven by local economic activity, right? Because, you know, demand and supply, nuclear creates jobs and investment, and housing prices goes up.
Yes, it's not only direct jobs in the nuclear power plant, it's all the supporting jobs and supporting industries. So, you know, there's a lot of added on benefit for the community from that. So what you find is that, you know, because people have got well-paid jobs and new industries, that the house prices go up, not down, and that's experienced worldwide.
Okay, a question from Michael. Okay, we've talked a lot about different technologies. What technology do you three think is the most appropriate for Taurong? And you can even go to vendors and model numbers if you want.
Yeah, so my view on this question is that for Australia, what we need to do is we need to find the design and the vendor that's most suitable for the country and that can be built in one place and repeated in other places. That's how we achieve the learnings, and that's how we achieve cost efficiency. The selection process for Taurong, I don't think will be just specific to Taurong, it'll be a bigger question. And what we need to do is we must remove the bans on nuclear energy so that we can start doing the work and put in place the processes and the authority to review the designs, to review the vendors, and to assess what is most suitable for conditions at Taurong, conditions in Australia, and most suitable for the future.
What I think will happen is that the studies will be done, as Stephen just mentioned, and a conclusion will come. We don't know what that will be. But basically I see two scale. I see the 1 gigawatt scale unit, and for a place like Taurong, and the other thing about them is that economics will drive you to build 2 of them rather than 1, to build them together. So Taurong could end up with 2 by 1 gigawatt units, and the other scale, the other small modular reactor scale, could be in the 300 megawatt range, and that could have a home in Port Augusta in South Australia, where where the load is a lot less, and Collie in Western Australia. So it's a bit of mix and match, and we need to optimise the arrangements for each of the particular sites with a common design, as Stephen's mentioned, to get the economies of scale.
You're good? I do want to make one point, because some of the different technologies, and there are many, have very different cost performance of construction, and we hear a bit about what's going on in the UK. Our Energy Minister likes to throw out the fact that Hinkley C in the UK is over budget, which is a twin EPR. So I've asked this around Australia and only 2 people have answered these questions. Does anyone here drive a Citroen? No. You probably don't, because they've got a horribly complex pneumatic suspension system, amongst other things. That's a bit of an analogy to the French designs of the EPRs. They're very large units and very, very, very complicated. Wonderfully beautiful things when they run. But does anyone have any other comments, Tony, on the experience in the UK, especially around how can we build on budget?
Yeah, we had a great time in the UK because we thought competition would be best. So everyone was a different design. So everyone had new problems and it was a nightmare. So one of the things that you've got to do is have this engineering organisation that looks at all the different designs worldwide and said, this is the best one and we'll build a fleet of these. We won't build a lot of different ones. You tend to be limited by the grid system. So places like South Australia, as Robert said, the grid's just too small for a big reactor. Queensland's good, New South Wales is good, Victoria's good for the bigger size of reactors. Western Australia, South Australia, etc., more suitable for the smaller sort of reactors.
Very good. Okay. What is the estimated cost of such a facility? Pick a unit and talk about the costs.
So what I'm going to say here is that this was another thing that I learned from the research that we did. The thing that surprised me was we looked at what made economic sense for the Australian electricity system if we assumed different levels of cost assumptions for building nuclear plants. And what we found was that as we increased the cost from, say, $5,000 a kilowatt up to 6 and 8 and even almost to $10,000 a kilowatt, we found that it was still economic to put nuclear in the system, particularly if you're trying to get all the CO2 emissions out of the system. So that really surprised me, the extent to which the model wants to pick nuclear. And the reason for that, when you assess the power system in a correct and rigorous way, is that the value of the power coming from those plants, the value to the system is so high that it's worth making the investment. And so I've come to the view that the first one will cost a lot to build, and there will be learning, and we may not be able to deliver it exactly on time and on budget like the Opal research reactor, but we need to be aware of that and then take the learnings from the first one, bring those to the second one. That will become cheaper and faster to build. And it's very clear that the value to the system is enormous, and that if we are serious about ultimately retiring the coal plants, that this is the direction we need to go.
Okay.
When I do my modelling, I typically use $8,000 to $10,000 a kilowatt for nuclear power stations. But what the modelling shows is that that's only it's a significant but small part of the total delivered cost of electricity. What is important is not the cost of the nuclear power station in isolation, it's the delivered cost to your house. And if we go down other routes with wind and solar, with its variability, we end up with added transmission costs and added distribution costs, and then we've got individual costs behind the meter of rooftop solar and batteries to keep it all together. What you find is that nuclear becomes the cheapest significantly when you look at the total delivered cost to customers.
Yeah, you really got to select a vendor who's got a proven design. What you don't want to do is the situation they had in France when they started the new EPR reactor and the design wasn't finished. And you can't design it and construct it at the same time. So you've got to start with a proven design, and then you've got to have a vendor that knows what they're doing, particularly with the supply chain, because you've got to get all the equipment ready and are onto site and built in the right order and at the right time. So you need a proven design, a proven vendor, not a first of a kind. This is what we call an N of a kind, proven design, and then you've got the best chance of building it to budget and time.
Robert, I like what you said there around the whole of transmission, whole of network costs. I think there was a report by Frontier Economics out only a couple of days ago that highlighted perhaps the fact that some of the numbers being thrown around in the political debate did not take into account the whole of system costs. That maybe, I think the headline was there's a $500 billion green hole in the current energy policy that we're not being told about. Yeah. Do you want to comment at all on Frontier's report?
I've read the Frontier report. It also doesn't consider all the distribution costs and the behind the meter costs. So it's looking at a large part of the costs, but there's still more costs to go. Right. And we need to look at all the costs.
Okay, all the costs. And David, next question. Points out, yes. How can we keep costs as low as energy alternatives and as low as possible? Now, I've already heard two things from you guys. One is build a fleet, so don't try and build all sorts of different ones. And the second thing that you might hear a lot about in the nuclear industry is first of a kind, or folk, and nth of a kind. So could someone have a think about that, comment on that?
How do we keep costs low? We design a power system that has a very efficient, high utilisation of transmission, of distribution, that has minimum requirement for behind the meter rooftop solar PV and batteries, so that we don't have to spend our own money. I don't want to get my electricity from the grid. I want it cheaply to come from the grid rather than have to generate my own. So there are many things that we need to do to keep costs low, and nuclear can help us do that.
Yeah, the key is considering the total system cost. So from a capital investment point of view and an operating point of view.
Okay, and you've just mentioned the home batteries, the cost of the batteries. What is assumed in the current energy policy around consumers buying the batteries?
Okay, when I do the sums on the integrated system plan, the rooftop solar requirement for houses, because not all houses can have rooftop solar because some are home units and they're just not suitable. The average size that I work out from the ISP requirement is 12 kilowatts, which is a huge amount. Most systems are going in like 5 and 6 kilowatts. Yeah. So we're looking at very large amounts of rooftop solar PV on basically every roof that's available in the country. And then we're looking at a 20 kilowatt hour battery, which is enough to power your house, to energise your house for over a day. And when you add those two costs together, without subsidies, it would come to about $40,000. So the plan is putting this enormous cost onto customers if it was to be implemented.
Right, so the numbers we're all hearing about in the media are assuming that we all each pay 40 grand for our energy network.
Fundamentally, those that have a roof suitable for rooftop solar.
Gotcha.
Yep.
Okay. From Kylie, how is nuclear good for the grid?
Well, it provides the stabilising foundation layer that lets you deliver reliable, affordable, zero emissions power to all the customers for all the reasons that Robert just described.
With a minimum amount of storage requirement. We don't need more Snowy 2.0s.
Okay. Or Burdekin pump hydro, yeah.
Because it's a rotating machine as well, it provides frequency control, so that the governor controls the frequency. So frequency control is something we used to get for free in the system, but now we're having to pay for, and we're using batteries to produce that system. But big rotating machineries provide system inertia, frequency control, stability, all the things we need to have a stable grid system.
Okay, next question from Brad, and this is an interesting question. This actually came up in one of our other sessions. Would the government consider giving the local community free electricity as compensation for having a nuclear reactor here? I've got a view on this too.
Well, I don't think any of us can speak for any government here, but I think that I think we'd have to think pretty long and hard before we did that. There is some conversations going on suggesting that if you're close to the plant, maybe you don't pay, all the full network costs. But my instinct is it's better to just price the commodity, at a cost-reflective price. And the thing is that if we can get the system back onto a rational place and a rational footing where we're not doubling and doubling again the costs, that we make it reasonable and affordable for everyone, then I think this issue will largely be resolved.
Yeah, I think that the key question there in the word doing all the work is compensation. And what that means is you're coming from a space where nuclear is still a bit scary and a bit worrisome. I think overseas you see when communities are completely comfortable with nuclear, you see local communities bidding for plants because they want them because of the future economic benefits and the very well-paying jobs that they bring. Anything else on that, guys?
Oh, just to say that one of those local little community things might end up with a 200 megawatt data centre.
Well,
and you just never know what industries might be attracted by that new nuclear power station.
So I made the joke down in Collie, which is in southwest Western Australia, a bit of a pot smoking area down there, and I sort of joked that the local community would go strongly into hydroponics. Okay, Michael, how old and what is the lifespan of the current distribution network from the Kingaroy station and the other 6 nominated sites compared to building the new distribution networks to all the new wind and solar sites, right? Do we need to upgrade the existing the transmission to use nuclear, and then how does it compare to renewables? Your slide sort of did a bit of this.
I actually did some work on the age of the distribution network in Queensland back in 2000, but I think it might all be out of date by now. But basically, you've got a very mature transmission and distribution network in this area, so it's going to be probably at least halfway through its life. But with the wind and solar, it's not just a matter of halfway through its life. We're going to need to double the capacity of these transmission systems because we're going to have to move power from where the wind farm, where the generation is, to the storage, wherever that might be. I showed you the example for New South Wales. The number of megawatt kilometres that you have to expend to make these systems work is enormous, and the costs are enormous. And a lot of the transmission and distribution networks are going to have to be simply rebuilt.
There's just one small point I'd add here, Jono, which is so that it's clear that there's a very strong logic to putting new nuclear plants on the same basic site, same location as existing coal plants for when they retire. Eventually, as Robert said, steel towers and the other assets reach the end of their life and need to be replaced. But one of the things that's really valuable that we must not forget is the existing easements, those corridors that host the transmission, that take a lot of planning and a lot of approvals processes and everything. That itself is a very interesting asset, and that supports.
And it's very interesting with Snowy 2.0. I mean, there's all sorts of reasons why that's delayed and over budget, but one of them is those transmission corridors through many, many, many landowners that are not so interested in it. Tony?
While we're talking about lifespans, there's a huge consideration with the lifespan of the generation. So we're seeing a lot of solar, utility solar, lifespan 20 years, wind 25 years. So all the existing solar and wind has got to have to be replaced before 2050. And we never see that costed. Whereas the nuclear power plants now, designed for a 60-year life, the first ones in the US have just been relicensed now for an 80-year life. So these are, long-term assets. And if we're looking at the lifetime of some of these assets, nuclear is really good in that respect.
Okay. Peter has asked, what is the time frame from the coal plant shutting down to the nuclear plant being up and running? I think there's another question coming, so I can skip over it. That says, can you build the nuclear plant while the coal plant is still operational? So we can talk about both.
Yeah, I think the logical thing is that you keep the coal plant going while the new nuclear plant next door is under construction. And when the new plant has been commissioned and brought online, then you're in a position to retire the coal plant. It's just common sense.
And I think the other bit of common sense is that none of these coal plants right across Australia should be closed down until there's adequate replacements. And those replacements are not appearing.
Yeah.
And just how much land does a nuclear power plant take? At Tarong, you've got 1,500 hectares. A Westinghouse AP1000 takes 10 hectares. So it fits in the corner of your plant.
You can put a few units in there. Yeah.
So there's no problem in finding enough land to build one at the same time as you're still running the coal plant.
Okay. What additional regulations are required in Australia over and above those of commensurate nuclear power generators in overseas countries, i.e. Canada? How does our existing regulatory regime compare to others, and what else do we need to do to beef it up?
So we've been a nuclear country since the 1950s. When HIFAR started up in 1958, it was the first reactor in the Southern Hemisphere. So we've had regulation of nuclear and all the safeguards and security, all the time. So this is one of the big things. We're not starting from scratch. We've got a nuclear regulator in our Panzer, we've got a safeguards authority in ASNO. They're both world class. We've got some expert lawyers in Australia. Helen Cook, you might have heard of, but she's done a lot of work with overseas countries looking at their regulations and transitioning to nuclear. And she's looked at the Australian system, and there's very little change required to make it go from what it is now to a civil nuclear power program. We party to all the international conventions already, so we tick a lot of the boxes. We're not starting from scratch. We can do this quite quickly.
So as you get the microphone, I think you're saying there it's not going to take us 8 years to set up our regulator, Tony, as might have been suggested.
So if you're really interested in this topic, the Chapter 3 governance in the UQ study looks at these issues and sets that out in detail. Australia is a founding member of the International Atomic Energy Agency. We're in good standing with all the treaties, as Tony mentioned. So we just have to do a little bit of work and strengthen and boost up the agencies, and so they have the right personnel to do the task.
Okay, this is a funny one. Is the federal government, from Veronica, is the federal government able to veto the state's current bans on nuclear power?
I think my understanding is, I'm not a lawyer, you're a lawyer, Jono, but my understanding is that is possible in Australian law under the Constitution for the Commonwealth to override the states on certain issues. I've also been told
Correct.
that it's possible for states to approach Canberra and say, we would like exemption from this particular law, or the people in our state, support that. So I think there's room for initiative and creative thinking and imagination, not to get trapped in this world of we can't do this because of the bans.
Yeah, we're going to lift the bans.
Yeah.
And we're going to lift the uranium ban too, by the way, people. Yes! Woohoo! Uranium. Okay, Greg, can a nuclear plant be built at Tarong whilst the coal plant continues? Right, that's what we said. That's yes?
Yes.
Absolutely, yes. Ross, what is the realistic economic benefit for Nangano? Sorry.
Western Australia.
Okay, I'm from Perth. Okay, I'm sorry. And when might those economic benefits start? So what do we see? Early investment in the community?
Where's Nanango?
Nanango.
It's just... Yeah.
Oh,
Yeah. So what do we get from early investment, early community benefits, other things like that?
There'll be definite economic benefits as the a new nuclear plant would be built, and that'd be obvious. But it will attract. I'm getting phone calls now from proponents for these data centres, and they would be very, very keen to set up right next door where the most reliable electricity supply will be in Queensland. And so the economic benefits, I think, will flow.
So there's a large construction staff when you're starting to build these, And then there's the ongoing jobs for all the operations, maintenance and support staff afterwards. Certainly, initially, it's a big project. It brings a lot of money and benefits to the area.
So we're going to see, how quickly can we see feasibility teams in community doing work on site if this policy is changed?
Well, I think as soon as investors see that the bans are going to be removed, I think we're probably starting to see early signs of this, then we'll see companies willing to start to put money into feasibility studies, concept and then pre-feasibility and feasibility.
Okay. Brad, I think we've had a Brad before. Who will design and build our Aussie reactors given that Australian businesses are lacking in competency? That's Brad.
So
Jeez.
this was the thing I alluded to in my talk, which was I thought it was too hard and we couldn't do it. It turns out that Australia's got a lot of capability and competency in nuclear. There's all kinds of people scattered all around. I keep meeting them who've worked in the nuclear industry in other countries who are Australians. They're engineers. They were involved in building the plant in the UAE, for example. There's people with UK experience. I bumped into the guy in the change room at Yoga. He's a English electrical guy doing solar inspections. Turns out he worked at Sellafield. So there's people all over the place, and I think that we can we can do this. That there's a mindset shift here, and remember that the Opal reactor, Tony's about to tell us, built on time and on budget. Who knows which country supplied the technology for the Opal research reactor? Does anyone else know apart from Jim? So Australian companies did the contract and the construction, but the design came from Argentina. So not America, not the UK, not France, not Japan, not Russia, not China, Argentina. And I would always ask my engineering students, raise your hand, please, if you think Australian engineers are less capable than Argentinian engineers. I've yet to find a single one willing to raise their hand to that question. Right, so we can do this.
Yeah, so for the Opal reactor, the core of the reactor itself, the reflector vessel, was made in Argentina. But, these are mainly civil constructions. So it was John Holland that did all the civil work. Evans Deacon did all the electrical work. Opal had about 70% Australian content, and that's the sort of thing we would expect with any of these nuclear power projects, because there's a limited amount of actual nuclear engineering in it. As we saw with the PWR, the back end of the plant, the turbines, condensers, pumps, feed pumps, air compressors, are all pretty standard equipment. You can buy and Australia can make. And eventually, of course, we'll be building our own reactors as well.
Okay, Michelle, how will it affect us, the landowners? We've talked a little bit about property price earlier, and also native wildlife and rural infrastructure. Now, we haven't actually talked about environmental offsets and impacts of a reactor.
Yeah, so I think the answer to this question is that these effects, to the extent that they're the kind of things you're concerned about, are tiny compared to the effects of the alternative. So if you go and look at what are the impacts on nature, wildlife, land, all of these things from the alternative, if you're trying to meet those goals, those targets, those emission reductions, while the nuclear ban's in place, these impacts are just enormous. I didn't realise how big they were until Steve Nowakowski educated me.
And actually the United Nations has a fantastic report on that very issue where they put all land impacts, water impacts, air quality impacts, carcinogenic and non-carcinogenic human health impacts everything into a big calculation, and funnily enough, nuclear comes out lower impact on everyone.
I think Will's been to visit the Diablo Canyon nuclear power plant in California, which is right on the coast, and there's whales and sea lions and, you know, abundant wildlife right next to the plant.
Oh,
and the same thing with a land.
Will tried to go and catch a three-eyed fish, and he didn't get one. From Cheryl, why was Tarong identified as a viable site?
I'll start off. There's an existing power station there, so that brings all the existing infrastructure. There's that grid connection, that big substation that's there. There's the transmission link that I showed you to Brisbane. There's the water resources there. I think most of the ingredients are there to build a nuclear power station.
Yeah, I'm going to add another one. It's got a local workforce who is absolutely energy intelligent, literate and capable.
Yeah, and that's what we did in the UK in the early days of nuclear. We shut down the small coal-fired power stations and retrained the staff. This is what Bill Gates is doing in Wyoming with the TerraPower project. You know, that there's a coal-fired power station there that's shutting down, retraining the staff. And, you know, this is what we want to do here, because it's, you know, if these sites aren't reused in an intelligent sort of way, then the local community is going to die.
Okay, now I'm just going to go off script for a bit because someone has asked a question through the QR codes. I'm super excited about that, and it's also about uranium. So I really am. Right, sorry, I'm trying to read this. Should uranium be mined, for example, under Kakadu National Park, where would there be any damage to the environment? If so, would the damage be minimal, or would rehabilitation bring Kakadu back to its natural state? Can I have a go at that one, guys? Yeah, okay. I think maybe people there are talking about Jabiluka, which is the sort of a parallel deposit to Kakadu that there has been a history of a potential mining on. And there's also the Ranger uranium mine in Kakadu, essentially next to it, that is going through a bit of remediation, and that is a problematic asset, right? And that was done in an open pit mine. So the question is, can you mine underground in a low impact environment? Absolutely. And actually, Ranger did have the Ranger 3 Deeps, which was an underground component, which if you approved the project today, you'd do it differently to what they did 50 years ago. And that's true in so many things around the world. So, I mean, I'm very passionate about our ability to mine uranium in a very safe, very environmentally friendly way. Mining uranium is the number one highest leverage thing we can do for Australians to help global decarbonisation, right? So we could cover Australia in solar panels. If we overturn the ban on uranium in Queensland and Australia, in Western Australia, and export that uranium, we could essentially meet net zero off the back of the implied carbon credit of all that green energy that we're exporting. It is that significant. Okay, my rant on uranium over. But if anyone wants to talk about it, I'm here afterwards. Go.
I spent almost 5 years working for what was then one of the world's major uranium mining companies.
You did?
Yeah. There's sort of three broad techniques for getting uranium out of the ground. One is an open cut pit, as Jono mentioned. The other one is an underground mine, which people generally know what that means. And the third one is what's called in situ leaching, which was pioneered big time in Kazakhstan, where and Jono knows about this.
We call it in situ recovery now because leaching is a bad word.
Yeah, okay. So it's a technique that's it's more similar to say shale gas. You drill down and you can draw out the mineral without having to go in tunnels.
Okay, so we never move physical dirt. So our project in WA is an ISR project. What's interesting about that is when people are concerned about uranium mining, and the unions they are concerned about worker dose rates. And in uranium mining, the vast majority of that can happen is when you physically mine dirt, and then you have to crush it because that's when you create dust, right? And in situ recovery mining, no dust because you never move dirt. You bring your ore into solution and already in a liquid form. So much better from an environmental and worker perspective. This is for you, I think, Tony. Thorium versus uranium.
Yeah, people get quite excited about thorium sometimes, but thorium isn't a fuel. You can't put thorium in a reactor and away it goes. So thorium is what's called a fertile material. So if you bombard thorium with neutrons, you can convert it into another form of uranium, which is a fuel. So it's uranium-233 instead of 235 that we're used to. In that conversion process, there's a few problems because the intermediate product absorbs neutrons, plus you get all sorts of other things, so you get a bit of dose with it. We think thorium, is producing less waste, but it'll only produce less waste if the neutrons to actually convert it are made from something that's not like uranium-238 and 235 that produce all this waste. So you've got to get through the thorium cycle to produce enough 233 to be able to then use that as a driver to produce the neutrons. So eventually you can get down to sort of lower waste, but it takes you a long while and it's quite difficult. Some of the more advanced reactors I think are quite interesting for thorium. Things like molten salt reactors. So there's experiments going on in China. They've got a thorium molten salt reactor they're experimenting with at the moment. So longer term, certainly thorium could be a possible. Longer term also, some of these more advanced reactors like molten salt are going to be important because they not only produce sort of electricity, but they can produce process heat, which is going to be very useful as well.
Okay, so I took out of that yes, in the future possibly, one to be built here if it's going to be built as part of the plan will be uranium. This is great, we're getting questions from the floor. I've got another one. It's not uranium this time. Can coal supply the same base load as nuclear? What is the cost comparison of that?
Yes, but if you were to try and, so it comes back to the CO2 emission goal, if you were to try and reduce the CO2 emissions from the coal, you'd have to do that with carbon capture and storage, and that would be probably as expensive or more expensive than nuclear. So coal freely releasing CO2 to the atmosphere probably be cheaper than nuclear, but once you bring that extra requirement in, then nuclear comes into the picture and becomes very competitive.
Okay. Now, you're right?
I agree.
Just one more comment as well. What we're finding with coal-fired power stations is, of course, they have to turn down in the middle of the day. And minimum load for a coal-fired power station can be quite difficult. You come down to a limited number of mills, and it can get a bit unstable. So coal is quite limited with its minimum load you can come down to, whereas a lot of the modern reactors are designed to load follow to quite low loads. So they've got some advantage in that way.
Okay, another question from the floor. This is great. Can a nuclear plant save the evaporated water for reuse and reduction of water usage, similar to cogeneration used in sugar refineries? Assuming, can you capture, instead of putting out all the steam out the cooling towers, can we capture that and recycle it?
Well, it is recycled. It goes up and drops back again, so it's automatically recycled.
Here we go.
Maybe the question to do with waste heat. There's also waste heat opportunities with nuclear and with sugar refining, that process as well, and maybe that's what the question's focused on.
And if someone wants to talk about the industrial heat capabilities in nuclear, now's a good segue.
Yes, it can be done. We can. The diagram that Tony showed with the waste heat going off, that heat can be used. It can be used for industrial purposes.
Yeah, the trick with selling heat is you need to be co-located, so the industry needs to be very close. You're not going to deliver heat over long distances. Australia probably doesn't have a huge amount of heat demanding industries like some other countries do.
Yeah. Okay, question from John Paul. This was from earlier. What legal and regulatory hurdles do the states and Commonwealth have to go through in order to implement nuclear power, and how long would this take as part of the process? We have been very clear that there's one section of the EPBC Act, which is section 140A, and there is one line of it, which is subsection C, and that says nuclear power station. It requires a very small amendment to the legislation for that, and actually you might want to at the same time get rid of section B, which is also which is enrichment, because we might want to do some enrichment at some time in the future. Other than the EPBC Act, which is a straightforward thing, what other legal and regulatory hurdles do the states and Commonwealth have to go through?
The ban, it's similar to 140A. That type of legal wording has been inserted in a few different places in Commonwealth law. And then there are bans in Victoria and Queensland and other states. So there's cleaning out work to do in the legislation, and then we need to put in place a set of regulatory arrangements for regulating a civilian nuclear power industry. So basically the regulatory arrangements we have at the moment were designed to regulate a research reactor. We're now, I think we've made, or we're very close to having made the changes needed for the nuclear submarine fleet, and then there'll be some legislation needed for regulating a civilian fleet.
Yeah,
it's not dramatic.
It's very interesting that supposedly it's going to take us 8 years to get our regulatory regime in place, but we've able to put in place a new submarine regulator, so there is a brand new submarine propulsion regulator literally being cooked up and ready to go now. Jocelyn, what successful examples can you share, and where's it gone wrong?
So when you're looking at nuclear power deployments recently, I mean, going back to the 80s, France hit the oil crisis, decided to build a fleet of nuclear. They were commissioning one every 3 months, big 900 megawatt reactors. So, you know, people have done it very successfully in the past. Japan had a very good program. Currently, the most successful countries are probably South Korea, because they've been doing a steady program of building all the while. But a newcomer country is the UAE, United Arab Emirates. So they decided to go nuclear. They decided at the moment they were using all their gas and oil for their own generation and desalination in particular. So they decided nuclear was the best. They then got tremendous support from the International Atomic Energy Agency, because they support any newcomer countries that want to start up. So they give them a lot of support and backing. So they looked worldwide at what was a proven design and what was a proven vendor, exactly as we would do. And they chose South Korea. So they chose KEPCO in South Korea. And KEPCO built 4 reactors on one site, on the Baraka side. And very successful projects, and they're all 4 now in commercial operation. So that's a very successful project.
Yeah, as far as new builds go, the ones that impresses me is the United Arab Emirates that Tony just mentioned. But the other place that I visited a couple of years ago was Ontario, Canada, and they've got a very impressive scheme as well with their CANDU reactors. And the CANDU reactors that were coming to end of life have been refurbished, and I think they're really on their way of producing electricity for their customers at about half the cost of what we're paying here in Australia.
Yeah.
And it's a key part of it.
Yeah. The CANDU refurbishment program is very significant, and it is being delivered under budget and ahead of time.
Yeah, okay. There was a second part of the question, guys. What's been unsuccessful? Because I've got one, and that is almost any build of an EPR, which has gone horribly over budget.
If you build one and then give up because the first one was difficult, and then you try and build a different one, and then you have the same experience and give, that's the recipe for failure. Building different ones one after another.
Another unsuccessful thing is interesting because it's going full circle is you'd never believe who tried to build a reactor about 20 years ago is the Philippines. And that reactor got pretty much built, it just never got turned on. And yet now the Koreans are doing a study to actually bring that into production for the first time because they're going nuclear.
Yeah, and another lesson is, and I think it was mentioned earlier, don't start construction until the design is quite mature. So if you, there are some reactors in the US where they started construction, they thought they had a 40% complete design when they broke ground. Looking back, it was really 20%, and that's a recipe for running over time and over budget.
Okay, we'll talk about running over time. That's us tonight. So thank you all. I'm actually now going to invite founder of Nuclear for Australia, Will Shackle, up here to say a few closing words. And just lastly from me, on the way out you're going to see a QR code which is about signing the petition. I know many of you in the room will have already done that, but if you haven't done it, please do that QR code on your way out. It means a lot. Thank you.
Well, firstly, thank you to everyone who made it out here this evening. Obviously, it was quite a long information evening, but we thought it was important that we had the chance to answer as many of your questions as possible. To continue with the thank yous, first of all, thank you to Jonathan. I found it very entertaining watching you back here in UMC this evening, and thank you to the three experts that have travelled quite some way, with the exception of Stephen, who's from Brisbane, to make it here this evening to share their expertise, to Tony, to Robert, and to Stephen. Thank you for all that you do. I'd make it clear that none of the presenters here this evening have been paid. They do this out of the goodness of their heart, their genuine support of nuclear energy, and I think that's really, really important. It's certainly a value that we share with Nuclear for Australia, being a grassroots organisation. In particular, I'd like to thank all of the Nuclear for Australia supporters here in the audience today. I've had an opportunity to meet quite a few of you, and I've really enjoyed that. If you would like to become a supporter of Nuclear for Australia, there is a QR code at the back. You can sign the petition to lift the ban on nuclear energy, and you'll therefore be part of our campaign, part of the 75,000 people who have joined that grassroots movement. And just to close with a few more things, first of all, as you can see behind me, we've got our fact sheets. So if you don't feel like we've been able to answer one of your questions today, the first place I'd direct you to is to our fact sheets. Not all of them have been released yet, because there's a lot of work that have gone into these, talking to experts, making sure that they're correct, but we've got fact sheets which address a lot of these concerns and questions which have been brought up this evening. You can access them by scanning the QR code up there. They're also available on our website, nuclearforaustralia.com. We apologise for not having printed versions of those for you to take home, but they are accessible on our website for you. We've also got social media pages where we share content more regularly. Let me just quickly look at my notes. I'd also just say that this is one of the first information evenings that we have held as Nuclear for Australia. If you have any feedback for tonight's event, please email us. The contact form is on our website. Our email is info@nuclearforaustralia.com. We're looking to hold more information evenings across Australia to help make sure that everyone is informed about the facts of nuclear energy and bring more experts like these guys across Australia to do that. So if there is any way we could improve, we really do appreciate that. To briefly look at my notes again, I think that is probably it. I've certainly appreciate this evening. Thank you again to all of you, and I hope you do enjoy the evening. And one last thing, I just forgot, the experts will be floating around at the end, so if you have any immediate questions, any